Let's talk about question 11 from our previous quiz. The question said, a multiple choice test with 10 questions has 6 possible answers to each question. Assuming you guess randomly, what is the probability of selecting the correct answer on all questions? I've done this calculation previously. Rather than redoing it, I'm just going to walk you through what I found one step at a time. All right, so in the first case, I'd laid out my conditions. I have 10 questions, 6 answers each, and I want to find the probability of answering all the questions correctly. There's 2 ways of thinking about this. One way is how many ways, and order doesn't matter here, because all I care about is what is the total number of questions that I got correct, not in what order did I get them correct or anything like that. There are kind of 2 ways to think about this question, and I'm going to describe it the way I thought about it when I first wrote the quiz, and then a way to think about it in terms of binomial distribution. So first thing I thought was probability that x equals 10, so all 10 are correct. How many ways can I get all the correct answers? And there's only one way. I have to answer every question correctly. So there's one favorable outcome, and then I thought about how many number of outcomes were there in total. So I know there are 10 questions. So think about it like a tree diagram, 1, 2, 3, 4, 5, 6, and so on. And I didn't worry about drawing the tree diagram. I just thought about how many branches or how many outcomes are there for each event. So the first trial, question 1, how many outcomes were there? There were 6. How many outcomes for the second question? There were 6, and 6, and 6, and 6, and 6. And I wanted to find all the different ways, or I had to count all of them. So how many ways can I answer question 1? And how many ways can I answer question 2? And how many ways can I answer question 3? And so it's an and question. So we use product rule. So I'm going to multiply. And so basically, that's where I came up with this formula. So I have one correct way of solving it, or one way of getting all the correct answers, divided by 6 times 6 times 6 times 6, 10 times. So 1 over 6 to the power of 10, which equals this number right here, or approximately 0.000017%. So if we want to think about it that way, that's fine. But let's take a step back and think about it in terms of our binomial distributions. So with our binomial distributions, I have a number of independent trials. This is just like our random quiz / test we did in class, where we had to talk about American politics and the Declaration of Independence and stuff, and we were randomly guessing. So it's binomial because each question has 2 outcomes, success or failure. Each trial is independent of the other, so whether I was correct on number 1 does not impact my probability or chances of being correct on number 2 or number 3, and so on. And so let's set this up like a binomial problem. We'll define a random variable, let x be the number of correct answers. We're going to use our familiar formula here. I'll just write that off to the side real quick. P of x is equal to, let me make sure I get my variables labeled correctly here. So P of x is equal to NCX, P to the x, Q to the n minus x. So all our choices, our probabilities, and our failures. So I set it up. There were 10 questions I was choosing from, and I wanted to get all 10 correct. So x is my number of successes. X is 10, because that's what we're looking for here. So 10 to choose from, 10 need to be correct. Probability of being correct on any one question, the probability was 1 out of 6, and that's unchanging. So that's another indication that this is binomial and not hypergeometric. So 1 out of 6. How many questions did I need to get correct? It was 10. Probability of failure in each question was the other 5 out of the 6 options listed for each question. So Q, or 1 minus P, is 5 over 6. And how many questions am I allowed to get incorrect here? 0, because I need to get perfect. So 10 minus 10 is 0. Plug that in my calculator and get the answer. And it's a little ugly because of the scientific, or we use scientific notation because it's a little ugly. It's a very low number. And so we see, if we simplify, or if we solve, 0.000017%. I also resimplified it here just to set it up in a way similar to how I first thought about solving this question. And what I did was I did 10 choose 10, and that equals 1. If there's 10 items and I want to lay it out, or how many subsets are there from 10 items? If I'm choosing 10, there's only one subset. It's the whole set. It's all 10. 1 over 6 to the power of 10 is the same as 1 to the power of 10. or just 1 over 6 to the power of 10. And anything to the power of 0 is just 1, so I didn't need to write that term. And so this actually looks familiar. This is what I started with when I approached the question the other way. I got 1 over 6 to the power of 10. And that's why I wrote here for myself, smiley face, same as on the quiz, because even though I approached the question 2 different ways using 2 different tools, I got the exact same answer. So that's pretty nice. And that shows us that there's more than one way to do this. Sometimes we don't need to use the formula. It's just a tool to help us get there. If we understand what's happening intuitively, we can take another approach as well, and that's fine. The other question we're going to look at is from page 385, number 17. A judge in a model airplane contest says that the probability of a model landing without damage is 0.798. So there is a 1 chance in 5 that any of the 7 models in the finals will be damaged. Discuss the accuracy of the judge's statement. So let's summarize. Probability of landing without damage is equal to 0.798. And the judge says there is a 1 in 5 chance that any of the 7 models in the final will be damaged. And so that also tells us, so we have a probability here, 1 in 5, and we also have the number of models that are being considered, which is 7. We know this is a binomial distribution because it's in the binomial distribution section of the book, but that's not helpful if we're just seeing this question straight up. And so what we want to consider is that the probability is not going to change as we do our calculation. So we are told that the probability of landing without damage is 0.798%. That's not going to change. Even if the first one crashes and the second one crashes and the third one crashes, we've already set this or calculated this from previous historical examples or calculation or whatever. We don't know. The point is that this value is not going to change. The probability is not going to change as we do our trials. So the trials are independent. So it's going to be binomial distribution where we're just concerned about success or failure as our possible outcomes. So let's see if we can set this problem up and kind of find a calculation that can prove or disprove what the judge is saying. As I've done before, I like to write the formula out to guide me as I set up my problem and define my variables and stuff. So probability of success is equal to NCX P to the X Q, or 1 minus P to the N minus X. Let's define our variables. N is our number of trials, and there are going to be 7 trials. X is our number of successes. And the judge says there's a 1 in 5 chance that any of the 7 models will be damaged. So any just means if there's 1 damaged. So let's try x equals 1. And nx, our probability of success, which is landing without damage. Well, let's change that. So let's let x be number that are damaged. So our probability of, well, let's find Q first. Our probability of not being damaged is 0.798, which means our probability of success, which is our probability of being damaged as we've defined it in this case, is going to be 0.202. Let's do our calculation and see what we get. And if we go ahead and do our calculation, 7 choose 1. So we have 7 trials, 1 success of failing. Probability of success, which is being damaged, to the power of 1. Probability of not being damaged, to the power of 6. Is going to give us a value of approximately 0.37, or approximately 37%. Therefore, there is a 30, or sorry, let's phrase it differently. Therefore, the probability that one model out of 7 is damaged is 37%. But this is a discussion question. They don't just want the answer. They want us to think about discussing what the judge said, and think about ways that this question can be interpreted as well. So we just found the probability that one model out of 7 being damaged is 37%. Is that equal to 1 in 5? Well, 1 out of 5 is 20%. 20% and 37% are not equal. So we would argue that the judge is wrong. So actually, let's answer the question. Let's just finish it this way. Therefore, the judge predicted a 20% chance of success, which in our case is failure or damage. 20%. I want to use the word probability here. I don't want to start using odds and chance. The judge predicted a probability of 20% that one plane would be damaged but a calculation finds that it is 37% and the judge is wrong. But there's another way to interpret this question. So we just found, what is the probability that one plane is damaged? But he didn't just say one, he said any of the 7 models in the final will be damaged. So what we actually need to do here is a longer calculation where we consider what is the probability that our x value is greater than or equal to 1. So I wanted to work through this calculation anyway to show us one way of interpreting this and one way of discussing our results. But I think we need to expand our understanding a little bit, and I think this is the way the book wants us to do it too. So we're going to find the probability that x is greater than or equal to 1. So what are all the different ways that we can have our planes be damaged here? Well, we can have one plane damaged, x equals 1, or, so we're going to add 2 planes are damaged, or 3 planes are damaged, or 4 planes are damaged, or 5 planes are damaged, or 6 planes are damaged, or 7 planes are damaged. And once again, we can calculate this directly using the direct method, but that's going to take a little bit. We can also flip it around and use the indirect method. We know that the probability that greater than or equal to 1 plane, these are all our successes, where we've defined success as having damage. Is there any way that we can have no planes damaged? Yes. We can have failures where x is less than 1, or in our case, x is equal to 0. And those are going to sum and equal 100%. So in order to find the probability of damage of at least 1 plane, 1 minus probability of no damage. So let's find that, and this is going to be equivalent to 1 minus, x can only have one value less than 1 in our case. It's a discrete distribution. It can't be decimals or anything. It's a number of planes. So we can set x equal to 0. So once again, just to remind us, let x be number of damaged planes. So we've defined success as damaged. Let's carry down our values from above. So I have the same formula, p of x, ncx, p to the x, q to the n minus x. My n value is 7 trials. My number of successes, so x is set equal to 0. My probability of success, where success is damaged, is 0.202. And my probability of failure, that is not being damaged, is 0.798. Let's calculate. Probability that x equals 0. Probability that no planes will be damaged is equal to 720. Success is 0.202 to the power of 0. And failure is 0.798 to the power of 7 minus 8. Or sorry, 7 minus 0, which is 7. Let's calculate and see what we get. And we get a value of approximately 0.2061, or approximately 20.6%. So therefore, the probability of no damage is about 20%. So what did the judge say? He said there's a 1 in 5 chance that any of the models will be damaged. Well, there's approximately a 1 in 5 chance that none of the models will be damaged, because we have 1 in 5 is 20% here. But that's not what we're asked to find. We want to find the probability of any of them being damaged, 1 or more, and that equals 100% minus 20.6%, which of course gives us 79.4%. So let's answer and discuss what this means. Therefore, the probability of 1 or more, remember last time we only found 1. Now we're expanding our definition here. We're talking about 1 or more being damaged. Model being damaged is 79.4%, which is much greater than the 1 in 5, 20% probability predicted by the judge. And if you check the back of the book, they have the same answer as well. We'll just read it as confirmation that we were correct. There is a 79% chance that at least one model will be damaged. And once again, the key word there is at least, where we had to consider 1 or more plane being damaged.